You're looking at one of the most important books ever written, Euclid's Elements. For more than 2,000 years, this was the textbook for how we understand math. But hiding inside its pages, inside its absolute logical perfection, was a single, nagging line that just didn't seem to fit. A tiny flaw that would drive the greatest minds in history crazy for centuries. So let's just dive right into this, because today we're going to unpack two totally different answers to that question. One story says that trying to fix this one line accidentally created whole new, strange universes of math. But the other story? It says there was never anything to fix in the first place, and that maybe, just maybe, we've been misunderstanding the very foundation of math for thousands of years. All right, so here's the game plan. We'll start with the 2,000-year-old problem itself. Then we'll check out the mainstream view, what I'm calling the axiomatic universe. After that, we're going to explore a pretty radical alternative, the fortress of reason, and see how you might just derive geometry from, well, nothing. We'll put them head to head and then zoom out to tackle the huge question this all points to. Is math something we invent, or is it something we discover? Okay, so picture this. It's around 300 BC. A Greek mathematician named Euclid takes on this massive project. He wants to lay out all of known mathematics in a perfectly logical system, building this entire world of proofs from just a handful of simple, rock-solid starting points. And honestly, he created the gold standard for logical argument that we still use today. But here's the thing. Among his starting points, one of them was, well, it was long, it was complicated, and frankly, it was just awkward. It completely broke the beautiful, simple elegance of all the others. For centuries, brilliant thinkers looked at it and thought, this has to be a mistake. This must be a theorem that Euclid just couldn't figure out how to prove. And they spent their entire lives trying to prove it for him. So this brings us to the mainstream story, the one you'll find in pretty much any textbook. This view treats math kind of like a game. You start with a few basic unproven rules, call them axioms or postulates. And then you just see what kind of world you can build from them. As long as your rules don't contradict each other, you're good to go. And Euclid's first 4 rules are just chef's kiss, perfect examples of this. They feel so simple, so self-evident. You can draw a line between 2 points. Yep. You can make that line go on forever. Sure. You can draw a circle. Of course. All right angles are the same. Got it. It's clean, it's elegant. And then came number 5. And there it is. I mean, compared to the simple, crisp statements of the first 4, the 5th postulate is a whole paragraph. It's dense, it's clunky, and it is definitely not self-evident. It basically describes when 2 lines will eventually cross, but it just felt so out of place. Yeah, this quote from one of our sources really just says it all, right? It captures that feeling that mathematicians had for centuries. It just feels wrong. It really feels like it should be something you prove from the other rules, not something you just have to accept up front. So everyone tried to prove it, and everyone failed. But then, in the 1800s, a few mathematicians like Bolyai and Gauss had this wild idea. What if you can't prove it? What if it's actually its own independent thing? So they said, okay, let's just change it. Let's see what happens if we assume parallel lines work differently. And, as one of them wrote, out of nothing, they created a strange new universe. And this is where the story gets absolutely mind-blowing. These strange new universes weren't just some weird math experiment. About a century later, a guy named Albert Einstein realized that this non-Euclidean geometry was the perfect language to describe our reality. In his general theory of relativity, gravity isn't a force pulling you down. It's the actual curvature of space-time. Massive objects literally bend the universe, and this new math explained it perfectly. And that's the mainstream story. It's an amazing story, but what if it's wrong? What if that whole 2,000-year journey was based on a fundamental misunderstanding? So now we're going to look at a completely different idea, one that argues Euclid's postulates were never guesses to begin with. This slide right here, this is the core of the whole alternative argument. On the one hand, you have a postulate, an unproven starting guess, like the rules of a game we just invent. But on the other hand, you have a requirement, a proven, logical conclusion, a fact that we discover through reason. You see the difference? It's not just semantics, it's a completely different philosophy of math. And the evidence for this idea comes from the original Greek. The word Euclid actually used was idemata. Now, according to this argument, that word does not mean postulate or axiom. It's much closer to something like as has been requested or as asked. The implication is that Euclid was referencing concepts that were already proven and understood. He wasn't making assumptions. He was building on a solid, pre-existing foundation. Okay, so if these concepts aren't just guesses, where do they come from? Well, this fortress of reason view argues that you can derive all of geometry step by step from literally nothing. So let's try it. Imagine a total void. No space, no objects, just a mind that can think. So from that thinking mind, the very first concept is born: location. Just a simple distinction between here and not here. Once you have two locations, reason tells you there must be a shortest, most efficient path between them. And that's a straight line. Now, what if you imagine a path defined by perfect symmetry, where every point on that path is the exact same distance from a central location? Well, you've just logically defined a circle. And if you slice that perfectly symmetrical circle in half, and then in half again, with two straight lines, you logically create four identical corners, right angles. See what's happening? There are no assumptions here. Each idea is a proven logical consequence of the one that came before it. And this brings us right back to that troublemaker, the fifth line. So what is it? Is it an optional rule in a game that we get to pick and choose? Or is it the final provable step, the grand finale, in this long chain of pure logic? This is the heart of the whole debate. So let's put these two ideas side by side. In the axiomatic universe, the fifth is a choice. And that choice leads to multiple equally valid geometries, some of which are essential for modern physics. But in the fortress of reason, the fifth is a provable theorem, the grand finale. It follows logically from those properties of lines and angles we just derived. And if there's no choice to make, that means there is only one true geometry. And the implication there is staggering. It means non-Euclidean geometry is a fascinating idea, but ultimately a logical impossibility. And just to give you a sense of how passionate this debate can get, the author of one of our sources, John Gabriel, puts it like this. From his perspective, even calling it the parallel postulate completely misses the point. He argues it's not a postulate at all, but a provable fact about angles, a property that follows directly from reason itself. So, as you can probably tell by now, this goes way, way beyond one line in an ancient book. This is really a debate about the very soul of mathematics itself, and it forces us to ask a really deep question that people have been fighting over for centuries. What we've really been looking at today are two completely different visions of truth. In one world, we are the creators. We invent different logical systems, like games with different rules, and then we just see which game happens to fit our universe best. But in the other world, we are explorers. We are discovering a single, unchangeable fortress of logical truth that was already there, just waiting for us to find the path. So that's the thought I really want to leave you with. Is math something we build, or is it something we find? Is it a set of tools that we created for ourselves, or is it the actual blueprint of the universe itself? Because the answer to that question, well, it changes everything.